Okay, oops, there we go. It's kind of what we're going to be doing today. We're going to be looking essentially at 7-7. There's only 6 questions, but they take forever in a day. And we're going to be estimating the area under a curve, which we've been doing. Going to introduce you to 2 new techniques. We know how to do a left 6, a right 6, and a midpoint 6. Okay, that's the kind of ones we've covered in the last day and a half. And we're going to look at 2 new guys called the trapezoid and the Simpsons rule. I'm going to show you a little bit of theory, you know, what they look like, how do you use them to get estimates for areas under curves. I'm going to show you a little bit of new, try and say that sentence, new notation, a way that we actually get you to find the area under a curve, and we do it in a much more symbolic way rather than just words, and we'll show you how that looks. Pretty straightforward, I think. And then we'll start this list where we'll set up the table, we'll add a little thing, how you label the information. We'll then do trapezoid rule, and we'll do Simpsons rule, and I'll talk a little bit about errors. So here is our basic problem. We have a curve, call it y equals f of x, done that a few times. And we're starting at some number x equals a, and we're finishing at some number x equals b, and we break this shape into, I don't know, 4 strips. And we've looked at how we can use the left-hand side, and that gets me L4. I can do the right-hand side, that gets me R4. I could choose the middle, and that would get me M4. All of them basically just get you the height of the rectangle that you want to use. So who are the 2 new guys? Well, let's do the trapezoid first. So you can imagine first person to deal with this problem says, okay, we've been using these rectangle guys, but you know, there might be a more efficient way of doing these strips. There's no reason in the world, is there, that they need to be rectangles. As long as I can find the area of the strip, I can make them any shape I like. I'll still have a strip. And the problem is the top, right? Everything in the bottom is pretty straightforward, but the top's a bit of an issue. So who it is, I have no idea. But they decided to make that shape. Would you agree that shape, which is, by the way, is called the trapezoid, hence the name trapezoid rule, would you agree that that shape is probably a pretty efficient shape for filling in a strip? Would you agree it's at least better than a rectangle? And so that would be our first strip, and this would be our second. And this would be our third. Oh, that one's almost perfect. And this would be my fourth. And we call these, this is called the trapezoid rule. And since there's 4 strips, yep, it's called T4. So you will be asked sometimes to estimate the area under a curve using the trapezoid rule. What they'll probably say is find T4, right? But that's what it is after. So you need to have a formula for it, right? You need to have a way of doing it. You remember you add the 4 on the left, that's L4. You add the, you know, the 4 guys on the right, that's the R4. You add the midpoint ones, that's the M4. So we got to figure out one of these guys, right? And I'm not going to tell you the formula yet, coming to that later. And then you would think, that's it. There's nothing better that you could come up with that you could find the area of. By the way, the area of these trapezoids, we can calculate them. I mean, if you wanted to do it the hard way, wouldn't you find this rectangle here and then add a triangle to it? I mean, you could do it. And can you imagine it's going to double your workload? Right, because for each strip, you'd have to find a rectangle plus a triangle and then add them up, right? So you don't really feel comfortable about doing it, but we'll show you there's a shortcut. Then back to my story. You would think they've kind of done everything that could be done? Well, actually, there is one last one that we deal with. Let's take 4 strips again. Each strip is not going to be a rectangle. Each strip is not going to be a trapezoid. What they did is at the top, from here to here, you put a quadratic curve through it. And you're able to find the area of this shape with a quadratic curve stuck in the top of it. You'd probably think, no way could I do that. Well, thankfully, somebody figured out a way to do it. And then the next strip, you do another quadratic curve on it. And the next strip, you do another quadratic curve on it. And the last strip, you do another quadratic curve on it. And these funny shapes that are strips with a little baby quadratic curve on the top, these guys are called Simpson's rule. We call these guys S4. Now, if I had the same curve and I looked at all 5 methods and I tried to put them in order of which one typically gets you the most accurate answer for the same number of strips, then what you tend to get is left 4 and right 4. They're the least accurate of them all, right? Sometimes the left is even worse, sometimes it's the right that's even worse, but they're kind of drawing. The next level up is actually trapezoid 4. The next level up is midpoint 4. So you notice the midpoint 4 is more accurate than the trapezoid. You notice that you might have thought the way things were going, it would be a little bit better. It's better than left or right on their own, right? It's better than them, pretty much guaranteed, except by flukes of numbers. Midpoint 4 is better, but the ultimate best one would be Simpson's 4. But left and right are easy to calculate. You haven't seen it yet, but trust me, Simpson's rule is very complicated to calculate, right? There's a lot of things in it to calculate it. So there's a kind of balance going on there. Now, if you're writing a computer program and you're lazy, do you know you'd use these guys and just do a billion strips? You know, you'd get the answer as accurate as you want. If you try to do it with Simpson's rule, you'd get a more accurate answer, but your program would have to be a little bit more difficult. And you probably say, ah, the heck with it. I'll just do left 1,000,000 and that'll work. So right now it's a big picture thing. We aren't doing any details, any number crunching, but this is kind of what's going on. Are we good so far? Use a trapezoid, use a strip, a little baby quadratic on the top. Now, just want to finish something that hasn't happened yet, but does happen. Guess I didn't do it because I didn't want to muddy the water too much. We are normally doing curves that look like that. And when we talk about the area under the curve, we're talking about that. You know that sometimes curves go below the x-axis. You know, like this one. You can still find the area under the curve. So we start here. Let's say we finish here. When you're talking about the area under a curve, here's something you do not get in physical world, but you are allowed to get in the math world. If any piece of the curve is under the x-axis, right? It's got negative y values, as this red bit here is. Its area is negative. How many times in your life have you been told you can't get a negative area? You must have screwed up somewhere. I'm now telling you, you can get a negative area. You have not screwed up. It is useful to consider areas below the x-axis as negative amounts. To give you a kind of example of what might look like, you recognize the sine function? If I did the area between 0 and 2 pi, wouldn't this piece balance off that piece? The area under this curve would actually be 0. If I only did this piece, the area would be, oh God, I don't know what the area is. Let me do it in my head for a minute. 0 pi would be 1. And if I did the area of the dotted one, it would be -1. Now you might think physical areas aren't 0. That thing is there. It's not, you know, a dot in space. Yeah, but we're not thinking physically here. We're thinking mathematical and area, right? And when we talk about it as area underneath a curve, right? So it's a different kind of area. It actually has meaning. Do you know if this was representing someone moving? Didn't they end up back where they started? So the area under the curve would represent what's called displacement if you do physics. And displacement is the difference between where you start and where you finish. Right? That's not the same as how far I walked. I could walk 200 feet, turn around and come back to my front door. Yeah, I've walked 400 feet, but is it my displacement still 0? Because I end up back at the door I started from. So I want you to try and think of area as more like that kind of measurement, right? It's like a difference in position, perhaps. But it is allowed to be negative. And I want to make sure you're clear on that, because it could happen that some of your areas under your curves end up being negative numbers, and it might freak you out to the point where you think, oh, I've screwed up somewhere. I'll try and fix something that's not wrong, right? Are we cool with the general rule about what's the most accurate and that negatives can happen? Okay. We have a lot of things to kind of do, but that's part of it. Okay, here's my little hit list. To do that, I need a question. Where did I put it? I had one set up. Come on, it can't be far. There we go. This is question 2.2 from section 7.7. I think there's 6 questions. You're going to find the area under the curve. It's y equals the sine of the square of x. You're going to do it from 7 to 10, and it's going to use 6 strips. And they're asking you to round off the answer to 6 decimal places. Except when you go and look at question 2, it doesn't look like that. It has a funny little symbol that looks like a musical symbol, and it has a 2 there and a 5 there. It has the sine of the square of x, and it is a dx. This is the notation that you use to tell people to find areas under curves. You want to write this, or you want to read this out loud, you say it's the integral from x equals 2 to x equals 5 of the function y equals the sine square root of x. Now, by you writing that down, it saves me having to say all of that. And you know how math people hate English. You see that? You could give to someone in China, someone in Czechoslovakia, anywhere you want, and they all use the same notation. Helpful, right? World is always helpful when we all do the same thing. Now, you then would write down n equals 6, probably with a little bracket around it. That makes sense, that we know that n equals 6 is just our shortcut for telling you 6 strips. And then they say, round your answer to 6 decimal places. We are not going to do our questions to 6 decimal places. I'm changing the question, but I fixed it so you don't need to worry about it. Why? Well, let me just show you why. That's what the table looks like if you do 6 decimal places. Do you want to add and multiply or do anything to numbers with that many digits? We are going to use 2 decimal places. Would you agree that's doable and at least you can live with it? Now, why am I not worried about that? If you can do this questions to 2 decimal places, can't you do the exact same questions to 6 decimal places or 26 decimal places? Isn't the only difference going to be boredom? Right. So I don't think I'm dumbing it down. I'm just trying to make it, you know, human, right? I just don't want you to, you know, hate math because you're getting frustrated with hitting 20 digits all the time just to get a simple answer. I've changed the software to recognize, fingers crossed, that we're using a different accuracy, and that's fine. Right. So ours is going to be to 2 decimal places. So let's set up this question. Well, whoops. First thing we have to do is we have to set up our table of values. And we know it starts at 2, so I'm putting that one in. And we have to calculate what width the strip is. And we call that B take away A over N. In this case, it's 5 take away 2 divided by 6. And that ends up being 0.5, which is quite a common width. Then I'm going to go and get all these numbers to make this table. And although I've got the values, you see them. Whoops, excuse me. You see them here, right? Let's just show you how to get them quickly. I think we're reaching the point now where it's really a good idea to use the calculator and the table of values thing, right? So I'll click over here. So that's what question 2 looks like, right? You see how it's pretty much that line there tells you everything, right? So I'm now going to, hopefully, are you seeing a calculator on your screen now? Good, right, that's just a little emulator. It's a little bit better than my calculator. So we'll clear this out, second, quit, and show you what we do. Right, y equals, you type in the function, as you'd expect, right? I just noticed something there. I hope it doesn't make a big difference there. Then I'll go second, table setup. And I'll start it, well, what number shall I start at? Ours is 7 to 10, right? So I'll start at 7. And delta x is 0.5. So I got that, and that's me done. I think I've mentioned it, but you know how WebAssign gives you different versions of the same question, so not anybody, you know, no 2 people are probably doing the same question. So the one that I've set up is actually being changed now that I went back into look at, but we're going to do the 7 to 10 one because that's what I got. So anyway, you set it up and you go second table, and there's all your numbers. And those guys will become 0.48, 0.39, negative 0.2. Do you see the first negative? Right, can happen. So a little bit of the curve is going to be under the x-axis. Are you comfortable about using the table setup thing to get your numbers? Because you kind of need those numbers to do anything. Are you comfortable about y equals and then setting the table up together? Maggie, you look puzzled. Are you okay?
I'm confused where we got the 7 and 10 because I thought we were working with 2 to 5.
Because WebAssign changed my bloody question after I made it. So we're going to be doing 7 to 10 now instead of 2 to 5. Right, that's all.
Okay, thank you.
So I should put that in, shouldn't I? Okay, let me return now. And you know, if I go back into WebAssign, it will change it again to 8 to 20, who knows, whatever. Right. So let's look at that set of values. So whatever ones I've got end up being these ones. Yay. Are you comfortable whatever the integral is? Oh, that's weird. I've never had that before. That's not meant to happen. Huh. I hope that's not technical issues. That would be annoying. Oh, good. That was weird. Right. Are you happy about where this table came from now? Right. From 7 to 10. Right. Your homework question might be 3 to 9 and 5 to 15, or who knows. So your table's going to look slightly different than mine. And that's basically number 1 done. How to set up the table. So far, so good. Now I'm going to put over here information we already know, but I want it in the same piece of paper. Remember how we got delta x? In this case, it's going to be 10, take away 7 over 6 strips, and that ends up being 0.5, right? So for my values, that's it. I think I may have, but if I've not, I'm going to show you. These x coordinates have labels. They have names that we use for them. The top one is called x0, then this one's called x1, this is called x2, this is called x3, 4, 5, and finally x6. And these are going to be helpful when I try and write down what the formula that we're going to use. When it was the left, the right, and the midpoint, I didn't really bother with this because it was pretty straightforward what you're going to do. It's now going to change. There are 2 guys that we need to do, right? Oh, by the way, that's me done step 2. I've labeled it. Now we're going to move on to step 3. Let's do the trapezoid rule. Remember the one that was a strip with a little triangle? You might think, oh God, this is going to involve us doing a whole load of rectangles plus triangles and doing it, 6 times, and I'll be here all day. Well, it's not that bad, but it's got its thing. Here is the formula for doing T4. You remember your delta x guy? Divided by 2. And then the value of the function at x0, which is this fella. And I apologize. I'm going to rewrite it over here because I need more room. And it's the first guy, twice the second guy, twice the next one. God, I'm going to have to write smaller. Twice the next one. Twice the next one. Twice the next one. And one of the last one. So if you look at that pattern, do you see that you use delta? I will pause some people right now. Excuse me, I'm hitting the wrong buttons. There we go. There we go. Right, where was it? Yeah, so it might look messy, but if you look at it, can you see that it is essentially I closed too many windows here. Can you see that it's essentially just one of the first guy, one of the last guy, and twice everybody in between? And do you notice that the delta x is now halved? Now this is a bit messy, but this is how you get, it won't be trapezoid 4 actually, this will be trapezoid 6, won't it? Because there's 6 strips. Okay, here goes. Delta x is 0.5 over 2. One of these guys. 2 of this guy. 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 And 1 of this guy. You know, if it's 2 decimal places, you could probably do it in your head like I just did. Right, now it's not by any stretch of the imagination a very easy thing. It's quite a lot in it, you know, it's not hard in that sense that it's difficult, but it's kind of hard because you have to be careful and there's a lot of numbers floating around. But these guys here, when we combine them, will give us our trapezoid 6. So here it goes. 0.5 divided by 2. Let me check something. 0.5 divided by 2. If you're not sure, stick things in brackets. There, bracket. 0.48 plus 0.78 plus 0.62 plus 0.44 plus 0.28 plus 0.12. Take away 0.02. And the answer we get is 0.675. Are we comfortable about the formula for doing a trapezoid? It's delta x over 2, 1 of the first guy, 1 of the last guy, and twice everybody else, all added up. And this guy will always be a left 6 or a right 6, right? So if you do 6 strips and you do a trapezoid, its answer is closer to the real answer than a left 6 or a right 6 is. Now, some people think this is interesting, other people don't, and that's totally up to you. But do you know that the trapezoid 6 is actually the same number as that? So if you ever get a question and it says find left 6, right 6, mid 6, T6 and S6, couldn't you just use the left 6 and the right 6 to get T6 without doing that formula? Unfortunately, they don't do that very often, but if they ever do, I would suggest you do it, right? We cool with that? So that is how you do the trapezoid rule. Pretty accurate, a little bit more awkward. You know, there's a balance. To get more accurate, it's going to be more awkward, right? It's going to be more detailed. The formula is going to get uglier. So we are now going to look at the Simpsons rule. I'm going to keep my nice little guy here because you use the same table, right? Isn't that the same table I would use for left 6 and right 6? Right, and I now use the same table for T6, and I'm going to use that same table for Simpson 6, right, S6. I wouldn't use that table for midpoint 6, wouldn't I have to do a little alteration as you've seen yesterday. So what does the formula for Simpson 6 look like? Oh, you won't like this formula. I think the trapezoid one, 1, 1, and 2 in the middle is pretty easy. Watch this one. Oh, just had the thought. Just hold a second. Cool little thought came to me. Where is it? Where are they? Where are you? Basic. Can never find things when I want them. Go away. No. Sorry for all this. Oh, got all the wrong windows in all the right places. All right. Hang in there. I'm actually typing some stuff here. Right. Don't know. Can you see the Simpson's rule formula? Okay. Oh, go away. Who wants to buy that, whatever it is? So make it a little bit bigger. Oh, maybe not that big. Delta x over 3. The first guy, 4 of the next guy, 2 of the next guy, 4, 2. So the pattern is 1, 4, 2, 4, 2, 4, 2, 4, 2, 1. In other words, you keep doing 4 2s until you get to the last guy. You see, that's quite a messy formula. I was hoping it was going to show you something quite interesting. You know the guy who is Simpson, who got the thing named after himself? Because everything else was named after the shape, right? Trapezoidal. That guy went to my university, Glasgow University, and that guy is Scottish. Come on, be impressed. All the best mathematicians are Scottish. Well, apart from me, because I can't count. Okay, that didn't work, but it was cool. Right. Oh, do you notice how easy it is for me to distract myself? Anybody who's had me before probably are getting used to it. For the new people who've not had me before, it's probably quite distracting. But anyway, lost my place. Here we go. It's this guy. 4 of that guy. 2 of the next guy. 4 of the next guy. 2 of the next guy. 4 of the next guy. And then you finish with 1 of the last guys. So that is going to be quite a messy calculation. Would you agree that you have to change how much you multiply each of the guys by? So this is just me. You don't need to do this if it doesn't make sense to you. But I tend to do a little rule. You see on my table, I just write down how much I'm going to times everybody by, just so I can keep track of them all, because I'm very bad at scanning back and forward. So what that is telling me is 1 of these, 4 of them, 2 of these, 4 of them, 2 of these, 4 of them, 1 of them. Okay, so let's see what that looks like as a calculation. 0.5 divided by 3 brackets. 1 of these guys, 0.48. 4 of these guys, I'm not going to risk that. 4 times 0.39. That ends up being 1.56. 2 of the next guy. 4 of the next guy, that one I can do. 2 of the next guy. 4 of the next guy. And 1 of the last guy. Whoa, just made it. Are you comfortable about how I'm getting these values? We're making no attempt, it's not in the course, of proving why this formula works, why it is what it is, right? I could have proved the trapezoidal, it'd take about 20 minutes. I'm not sure how much benefit you'd get at the end because you're just going to use it anyway. But here, I'm not even going to attempt to prove it to you. So you got all these guys, and now it's definitely a calculator job. So 0.5 divided by 3. Oops, let's do my little safety thing. Oh, let me show you why I do that dividey thing. If I went 0.5 divided by 3 times 6, just for argument's sake, you see the answer? It works. What I was frightened of that it would, ordinary calculation. So whenever I'm not sure, because I'm very careless, I put it in. Actually, in this case, you don't need it. 0.48 plus 156 plus 61 plus 88 plus 28 plus 24 and take away that guy. And the answer we get is 0.67. That's not bad. I'll put beside it T6. You see they're pretty comparable. Now, I'm not really comparing like with like here. Well, I guess I am. Yeah. It looks to me, would you agree that the answer is probably around about 0.67 something? You curious to know what the real answer is? Right. So am I. So let's show you how to find it. There's a way to get the calculator to find the area under the curve. You type in, well, I'm there. That was weird. Oh, you type in the function. Oh, I know what's happened. I'm using my calculator now. It was the sine of the square root of x. You go to window, and you do 7 to 10. You then go to, well, I do this. You don't need to. I do graph. Okay, you're just being awkward, are you? Okay. Take that guy in, you do the window, and then you do zoom to fit. There we go. And it's not a very interesting graph, but you see it. You can then do second calc, choose number 7, tell it to start at 7, to finish at an x value of 10. There's the area under the curve, and the answer is 0.676. 0.676. Just to prove me wrong, that's actually a better answer. But it is what it is. So, happy with Simpson's rule, trapezoid rule, midpoint. Now, the only thing that is going to change is that table. Can you imagine the next time it's going to be x cubed plus 1 from 5 to 15? Or e to the x over x from 1 to 7 in 10 strips or 4 strips. But really, once you've got the structure set up, it's all about getting that table. Once you've got that table, you can do a Simpsons, you can do a trapezoid, you can do any any guide that you want, and you will be, your answer will be correct. So let's look at error now. The last thing on my list. Well, the error is basically the real area, take away the estimate. And my order of accuracy is still correct. And so you're going to have, let's say 6, L6 and R6. Then you get trapezoid 6. Then you get midpoint 6. And then you get Simpson 6. Now, in the questions that we've got, just to prove me wrong, but that's life, the error in the trapezoid 6 was 0.001, and the error in Simpson 6 was 0.024, which you might say, well, that's a contradiction in what you just said. This is a general truth. Do you know, just by the flux of numbering and rounding off, can't L6 end up being perfect just by sheer coincidence? So what this is a truism. In general, if you do it, it's true. The more strips you use, the more this becomes true. So if I did 60 strips, I'm not going to do it, but if I did 60 strips, will you trust me that this one will end up being better than the other one? Think of it as a silly way. If I did 2 strips, couldn't any of them, they're all bad, but couldn't one of them be less bad than the others? And it's not really disproving what I just said, right? So you will get questions that says to you, which one is the most accurate, right? Out of, maybe they'll give you 3, midpoint, trapezium, and 6. Actually, if they give you midpoint, trapezium, and 6, well, you always do it in that order. Midpoint isn't, oops. If they do that, that will be your order, right? We're almost finished for today, so I feel a little bit like that chemistry professor who takes the green liquid and the blue liquid, and he says, look, I'm going to put these together and it's going to turn red. And you're all going to shake your head and say, nah, that's never going to happen. And he's meant to put them together and suddenly they go red and you're all going to go, wow, that was cool. And then he goes on and explains what chemical reactions made it happen. I feel a bit like I put them together and said, look, it's going to go red, and it ends up being yellow. And I'm trying my best to pretend that that yellow is kind of reddish, right? So yes, I know that this question, trapezoid 6, was actually more accurate than Simpson 6. I understand that, but I'm still correct in this, right? So it's one of that, you gotta believe me. You'll do enough of these that you'll get 5 out of 6 where what I said happened, right? And I just got unlucky with the one that did. Any questions before we go? If not, say hi. Remember, for attendance, say hi, and then bye-bye. Hey, we learned some cool stuff today, did we not? James, that was a very half-hearted nod. We learned some cool stuff today.
Well, I was trying to get my calculator to do the thing, but I keep getting a data type error.
What, you're trying to make it do all of Simpson's rule?
No, just the piece at the end where it did the calculation for the area under the curve.
Oh, okay. Let me show you that again, because I kind of jumped around all over the place. I'll do a different curve just to make life easy. Okay, so let's just say the curve was x cubed, right? Plus 1. And let's suppose we're going to get the area from 2 to 5. Right, do that. Then the thing that I played about with is zoom 0. That just gives me a decent window. Okay. Zoom 0. And then you go to the calc button. So it's blue button. Oops. Darn it. Blue button, calc. And you choose the one right at the bottom. Do you know that funny, looks like a musical symbol?
Yeah.
Right, oops. So you pick that one and you hit enter and you tell it to start at, darn it, what did I start that table at? 2 to 5, okay. So sit in calc, you choose that guy, lower limit 2, press enter, upper limit 5, press enter. It does a little animation thing, and then it tells you the answer is 155.25.
Yeah, that worked. Why? So I had
Well, you
sine
make,
square root of x,
well,
and
you
it had
make,
like a data type error.
right, so if you're doing it, it was sine is the square root of x.
Yeah.
So hit sine,
Mm-hmm.
square root symbol, x, and close a couple of brackets. Oh, and make sure that you're in your mode is radians, not degrees or whatever.
Yeah.
And if you did that, it should be fine.